Well, hello and welcome back to my video series on my flip dot display panel here. So in the last video I showed you the panel and we went over to the bench and we used the power supply to directly flip some dots by applying some voltage to the row lines and the column lines. Today I want to talk about the controller board on the back here. This panel is made with two different connectors here. There's a row connector here and a column connector. And so what I did is I made two separate circuit boards here, the one that plugs into each connector. It turned out to be a really convenient way to do it, in no small part because the PC board manufacturer that I used offers this size as their cheap prototype size. This is 10 centimeters square, and it's only $5 to get 10 boards. So it was much cheaper to make two separate circuit boards that size than to try to make one big board that would cover both connectors here. And of course there's an additional reason I want to try to do it that way. Usually you use these flip dot panels in a group. Often you have more than one. This is the one that I bought on eBay after seeing my friend's score on eBay from that same seller here. And of course what we're going to want to do from time to time is put these two together and drive them as one big panel here. So I wanted to make sure that the controller would be able to support that. I can show you what's on these two boards here. The main one, the one with all the intelligence here, is the row driver, and that's got an Arduino Nano right there, which is the same as an Uno, just in a small form factor here. And it's got a little power supply section here. So this whole thing runs on 24 volts, so there's a 24 volts DC supply that plugs into that jack. And then there's a 5-volt regulator there to power the Uno and the logic chips on there. And the power is daisy chained across this little connector here to get to the column board. And what the row driver does is it shifts data out to some shift registers here that are connected to the row lines, and then there's a serial connection over to the column board here to shift data out through this guy. These are just shift registers and drivers here. The column board has much less on it than the row board. It's nothing but the shift registers and some driver transistors here. But it's done in such a way that I can daisy chain multiple panels together. So if I want to use this panel in conjunction with this other panel, all I've got to do is put a column driver board on it, and then I use a little ribbon cable here for the serial column data, and I could daisy chain as many of these as I want. And then of course the other component is I need to get the row signals over there, and for that I just use a 40-pin IDC connector to just parallel those row signals over there. So the row lines are common across as many boards as you have connected together, and there's a separate column driver for each one. Now let's talk about what that circuit is, how you might want to drive this if you were using, say, just discrete transistors. So you remember from last time, this is what's on the panel itself. These are all the coils, and then there's a pair of diodes for each coil, and the coils are connected with common column lines, and then for each row there's a pair of lines, a high line and a low line. And the way you drive this is you would put a high voltage, for example, on the row 1 high line and a low voltage on column 1, and that would flip row 1, column 1 from one state to the other. If you want to flip in the other direction, you put the positive voltage over on the column line and the negative voltage on the row low line, and it'll flip back in the other direction. So if you were to do that, if we were to just examine one coil, think about how you might want to do that just with some discrete transistors, you would do it like this. So this is my coil and my diodes, and I've drawn in 4 transistors here in what's called the H-bridge configuration. This is really common for solenoids and motors and things like that. I've got 2 NPN transistors on the bottom here, and when you energize those by putting in some base drive there, that what you'd be doing is shorting the collector to ground. And on the high side here, if you were to reduce the voltage on the base from down below 24 volts, you would energize this transistor, and what you'd be doing is connecting this collector line up to 24 volts. So if you want current to flow, for example, in that direction, you would energize this transistor and this transistor. And if you want current to flow in the opposite direction, you would energize the opposite pairs of transistors. Now, of course, when we do this for real, we don't want to use a bunch of discrete transistors. We want to use integrated circuits. And an obvious choice for this with all these lines to control is going to be a shift register. So a really common shift register that you see all the time in Arduino circuits is the 595, the 74HC595. That's an 8-bit output shift register, and it's got, of course, a serial line in, and it's got a serial line out so that you can daisy chain the next shift register, and it's got a clock line where you apply pulses to shift in the data, and there's a few other control lines to deal with. Now the standard 595 isn't really suitable for this, at least not very, because it gives you standard logic level outputs. The output is either 0 or 1, 5 volts. And of course we have a 24 volt supply. Now fortunately they do make variations of this that are a little more useful. So one of them is the Texas Instruments 6B595. What's neat about that is the outputs, rather than being standard logic level, are actually open drain transistors. They're I'm going to draw them as BJTs here, so they're open collectors, just because I find BJTs easier to draw. But in each case what you've got is internal to the chip, there's the output transistor, and the collector. That transistor just goes straight to the output pin. There's no other circuitry there. So what that means is if you shift in a 0 bit to that bit location, that transistor will be turned off, and that output is actually not pulled high or low. It's allowed to float wherever it wants to float. And when you shift in a 1, that turns the transistor on, and then that pin is now pulled hard down to ground. So that actually turns out to be a little more useful. You'll notice if we go back to the transistor circuit, there really are 3 states for this. I can drive either side of this high, meaning connect it to 24 volts, or I can drive it low, meaning connect it to ground, or I can just not drive it in either direction. It's just off. So it really is a tri-state device. When you've got a shift register like that, obviously if you need 3 different outputs for each pin, you can't do it with just a single bit. A single bit would only give you 2 outputs. So in order to get 3 outputs, what I do is I pair up the bits on here. So each row line or each column line really corresponds to a pair of bits coming out of here, so that I can support the states of high and low and off. Now of course with 2 bits I get an extra state beyond 3. I get 4 states, and it turns out we need to ensure that we don't inadvertently end up in that state. There's a lot of ways things can go wrong with these panels, and I've discovered them all, and that's one of them here. So what I'm using is the 6B595 shift register, which is 8 bits per chip, and I'm using them in pairs of 2. So one of them, arbitrarily, I'll draw this one here, is the low driver, and I don't really need to do much of anything there. When I switch this transistor on, it's going to be shorted to ground, and that effectively is this guy right here, or this one over here. It works the same on the row or the column. If I want to drive high up to 24 volts, it gets slightly more interesting here. And what I've done is use a separate chip that has 8 high side driver transistors in it. So inside the chip, effectively, there's a PNP, and again, of course, it's in real life it's a MOSFET. I like to draw BJTs. And then there is some driving circuitry on the gate here, which I'll just represent with that rectangle, so that I can drive that from a logic level. If you put a logic 0 in there, this output is off. If you put a logic 1 in there, that output will be switched up to the positive rail, and then this just runs on the 24 volts. So the way that this works is there's a pair of bits in here. I'll draw the transistor in here. One of them is the low side driver, and the other one is the high side driver, and that goes over here like that. Now of course over here this is just open collector, so if I've got this transistor switched on, it'll be pulled down hard to 0. That's a logic 0 over here, that turns that off. If I shift in as 0 here, I need this to turn on, and with an open collector, what you need to do is put in a pull-up resistor. So on each of the high side lines there's a pull-up that goes up to the 5 volts, and that's a 10K resistor. So when this transistor is off, when I've got a logic 0 in here, this line can float up to the 5 volts because of that pull-up resistor. That turns on the drive on this transistor, and I get my 24 volts out here to act to be the high side. Now you got to remember that over on the panel here, I'm going to have the high side driver and the low side driver connected either through just this pair of diodes, or they're going to be directly connected if it's over on the column side here. So you can run into trouble. So these are effectively connected on the panel together like that. You would run into trouble if you tried to simultaneously energize the low side drive by turning that transistor on and the high side drive by turning that transistor off. You would be shorting your power supply together. So this 0-1 state is a forbidden state. We can't allow that to actually happen here. And if you're like me, you know in software development you can make all kinds of mistakes and bugs, and you might inadvertently shift out a bunch of 0 and 1s and blow every line at the same time. You want to make sure that doesn't happen. And so we want to have a little bit of a hardware safety in there to prevent that. And it turns out that a simple thing you can do to prevent that then is just put a diode in here. Just an ordinary, ooh, that's messy. Let me redraw that. I like neat diodes. Draw that, and boom, boom, boom. That's a little better. So there's simply a diode pointing down here from the high line to the low line. And what happens there is if you should find yourself in this state, this transistor is energized and this one is not, the combination of the diode and the pull-up resistor is effectively going to keep this line from going high enough to turn that transistor on. Of course you'd have just about 0 volts on there. You might have maybe 1/10 of a volt, and then you'll have a diode drop above it appearing on that line. So let's say maybe 0.8 volts, but 0.8 volts is not enough to turn on this high side driver here. So just to summarize all the states here, there's 2 bits for every line. I've drawn it here as if it's a column line. If it turns out to actually be a row line, the only difference is that you're going to have that pair of diodes in there in between, and that goes off to the coil over there like that. But effectively you'd be in the same boat if you manage to have the 0-1 configuration here. You'd effectively be shorting your 24 volts to ground through a couple of diodes. But again, this protection diode over here keeps that from happening. So now if we look at what the 4 possible states are, we could have both of these driving transistors turned off, and so the low side will be off and the high side will be pulled down. Let's see, no, this transistor will be off, and so this will be pulled up through the pull-up resistor. So if we make a little truth table here, 0, 0, 0, 1, 1, 0, 1, 1, what we're going to get on the output is driving high. 0, 0 drives the output high. If we have a 0 and a 1, that is our forbidden state. This transistor will be on, this transistor will be off, but because we've got the pull-up and the diode, this is also going to be off. So this is effectively a low state. It's forced to low from the disaster state. This diode turns it from disaster to just an ordinary low state. If instead we have a 1 and a 0 here, this transistor is turned on, which means pulled low, and so this high side input here will be off. The output 24 volts will be off. We've got a 0 over here, so this transistor is turned off, so there's no low drive, there's no high drive. This is our off state. And then the final condition is when we have a 1 and a 1 shifted in here, both transistors are turned on. So this one is on, we have our low line, our low drive through this transistor here, and this one is pulled down to keep this guy off, so this is the low state. So the difference between these two is this is the official real low state that we're intentionally shifting in with a 1 and a 1. This is the low state we get when we accidentally shift in a 0 and 1, which would, without this diode here, would be the disaster. So this is pretty much the heart of it. Whether it's the same whether you're driving a row or a column. The only difference is if it's a row, these diodes are effectively in there. These are the diodes and the coil that are on the panel itself. And when you've got the on the column side, there's no diodes on that side, but this is going to be the other side of that coil. So that's about all there is to it. That's the heart of it. So now I can show you back on the panel itself what's what. I'll take this guy out of the way so you can see. So we've got the power input over here, we've got the Arduino. These four guys are the 6B595 shift registers. This is the row driver, so I have to drive 16 rows, which is 32 lines, so I need all 32 bits. So I need 4 shift registers. And then for each pair of bits coming out of the shift register, there's a single high side driver, and this chip gives me 8 of those. So I only need 2 chips there. So basically I get serial data comes out of the Arduino into the shift registers. Every second line of the shift registers goes up here, and then up here it pairs up with its the low line pairs up with its buddy, the high line, and it's connected to these pins up here. Now I have got these extra protection diodes up here, and it turns out they're not strictly necessary. These are diodes that I put on the output side like that, going up to the 24 volts, to deal with the kickback on the solenoid coil. As you know, when you drive a solenoid, you turn your transistor on, you start driving current through it. But once you flip that driving transistor off, the voltage on that is going to want to flip around in the other direction and spike way up. If you don't have a diode to protect the circuit that's driving that, you can blow the transistor. So what I've done is individual diodes on the high side lines to act as that shunt. I don't have the corresponding diode on the low side. I'm trying to draw a diode with dotted lines because that's actually taken care of in this guy. It turns out if I'd read my data sheet a little better, I would have realized that effectively this diode here is already in the high side driver. So these really are superfluous diodes. I really don't need to have them in there. I was being extra careful, but that's turned out to be the least of my mistakes. That didn't really cause any harm. Just parts on the board I didn't really need. Now as for the column board, that's got nothing but the shift registers. It has 8 shift registers. I need to drive as many as 30 columns, and so and each takes 2 lines. That's 60 lines right there. So I need at least 8 shift register chips. And of course I need 4 corresponding high side transistor drivers. So what happens is the Arduino can shift data either into the row shift registers, or it shifts it into the column shift registers over this cable here. So this cable carries the data in, and the clock line and the control lines that you need to latch the data and whatnot in the shift registers there. So the way that you drive a configuration on the board like that is you figure out you've got to do it 1 row at a time, and you'd shift out let's see, no, I said that backwards. I need to shift out on the I need to energize a single column line and then energize as many on the row as I need to flip. So what I'm going to do is shift out across all my columns. I'm going to shift out a single bit pattern to energize just one of the columns, either high or low, depending on which way I'm flipping. And then on the row lines, I can shift out all 16 lines, either high or low, depending on which way I'm going to flip. You can only flip dots in one direction. You can flip more than one dot at once, but you got to flip them all in the same direction. So I can put a positive on multiple row lines and then put negative on a single column line, and several dots will flip one way. Or I could put negative on several row lines and then positive on a single column line, and the dots will all flip back the other way. Now I cheaped out a little bit. Should have taken a lesson from my good friend Brian, who did a little prototype driver for this before I even started. And his had a proper low side transistor driver, and I'm a cheapskate. So I thought, well, I can get away without that, because the 595, that's got a peak current of 500 milliamps. I figured, well, that's got to be plenty to shift a whole line. And it turns out if you do a whole lot of shifting rapidly, which I want to do, the 595 doesn't really like that so much. So if you're shifting all 16 rows at once. So it turns out for safety's sake, what I've got to do is actually divide up all of the rows into the odds and the evens. And first I shift all my odd numbered rows, and then in a separate operation I shift all my even numbered rows. So really to drive it, there's really 4 phases in the drive. The first phase is I'm going to drive odd numbered rows positive. In the second phase I'm going to drive even numbered rows positive. And the third phase I'm going to drive odd numbered rows negative. And in the fourth phase drive the even numbered rows negative. So I've got to figure out, based on the 16 bits I want to display on there, I've got to split them up into those 4 phases, and boom, 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 boom. If I'd been slightly less cheap and not quite so, another concern is it's not just being cheap, is I was concerned about having enough room on the board to route everything. I think in retrospect I should have been able to do it. Maybe in version 2 I'll give it a proper low side driver. But even with the proper driver like that, you still need at least the 2 phases, because you can't drive bits simultaneously in one direction and the other. You've got to do all of your flips in one direction and then followed by all of the flips in the other direction. Now the last little bit of this board that I want to talk about is the circuitry that's up in this corner here. And this is my column detection circuit. Now if you recall that these boards come in 2 different sizes. I've got a 30 column version and I've got a 25 column version. And so this controller could be on either one of these. And in fact sometimes we'll be connecting them together like this, and sometimes connecting them together like that. You can put them together in all different ways. And I wanted the controller board to be able to figure out what kind of board it's on, figure out how many columns it's got to work with. Because even on the 25 column board, the driver still has 32 bits worth of columns to shift through. And if you're going to, particularly when you're going to put 2 boards together, you've got to take account of those gaps. There's bits in the shift registers that correspond to bits in the panel that just aren't there. So if you want to shift something smoothly across the panel here, you've got to take that into account. And I didn't think it would be very elegant to have jumpers or switches or some kind of configuration in software that you had to do just to move the controller from one panel to another, or to rearrange these. I wanted this to be as automatic as possible. You just put them together, turn on the power, and then it figures out how it's connected. And so that's what this up in the corner is all about. So this IC here is an Opto Isolator, which is a combination of a diode, or an LED rather, light emitting diode, and then a phototransistor. So it responds to the light given off by the diode, and those pins come out. And so if you put some current through the LED and light it up, it'll turn on the transistor, and then you can see that from out here. So the way that this works is, the plan for this is that when you first turn the power on, the controller will turn off the row drive everywhere. So these are all just floating. And what it's going to do is turn on the column drive high on every column. And what I do is I pick any one of the low row lines. It doesn't matter which one you do. Let's say it's this one here. Row 1 low, and that line then comes in here to the Opto Isolator. So that's row 1 low. And then I have, what do I have? A transistor here, so I can switch this on and off. Boom, boom. And this line goes off to the microcontroller to flip that on and off. So when I turn on the power, I shut off my row lines and I set all the column lines to high. And it turns out it's easy to do just by flipping the enable bit on the shift registers there. And I turn this guy on so that now, and of course there's a resistor in here, so now that 24 volts is going to make its way from the columns through these coils and through these diodes to that line. So as long as any one of these is energized with 24 volts, that's going to appear over here on all of these row lines. And that's going to light up this diode, which is going to energize the transistor, and then this has a pull-up resistor over here to 5 volts, and this line goes out to the micro. And so what that can tell me is, as long as any of the columns is activated, I'm going to be able to sense that on the microcontroller. So initially I set all the lines to 1s, and then what I start to do is I shift by one column. I shift off, oh, I don't remember if it's right or left, but I shift off, let's say I shift off this guy. So I'll start off, all of these will be energized at 24 volts. I should hold it up here. All of the columns will be energized at 24 volts, and I can sense that through the Opto Isolator there. And then I shift by 2 bits, and it takes 2 bits, remember, for each column. So what I do now is I've turned off one of the columns, and then I sample that line again. Do I still have active columns? And I shift by 2 bits, and I just do that in a loop until eventually I've shifted out the very last column, and now this line I can sense that there's no more active columns. So now at least I know how many columns I might be connected to. Now, not necessarily all of them were active. I've got to now energize columns one at a time and figure out where my gaps lie. So then what I do is I shift in a 0 and a 0, which corresponds to turning column high, the first column here, and I look at my line, and if I see that that line is asserted, then I know there's really a column there. And then what I do is I simply shift by 2 bits. I shift in an off condition, and so now I'm energizing the second column, and then I'm energizing the third column, and the fourth and the fifth. And each time I just take a look at that line, and that way I can easily figure out exactly which shift register lines correspond to real columns in the row. And then I just save that information in a little array, and that is the magic that lets me put these together in any order. And on power up, it's going to figure out exactly how that works.